In the last video, we saw the turbulent viscosity for closing Reynolds equations for modeling Reynolds stresses using Newton's law of viscosity based stress strain relationship, where we introduced a term called turbulent viscosity. And turbulent viscosity on making a dimension analysis can be expressed in terms of and k epsilon, turbulent kinetic energy, and the dissipations. These two things have a separate transport equations called k epsilon equations, and the model for closing these turbulence uh, uh, Reynolds stresses is termed as k epsilon model. And we have several empirical constants, and since it's transport equations, we need to improvise boundary conditions. And we saw in different boundary conditions what are the setup that can be made for this k and epsilon values for different boundary conditions. For example, for inlet there should be a distribution of k and epsilon, and Newman boundary conditions may be expressed for the outlet, and for stream you can have a Dirichlet of value 0. So for the solid walls, we saw that there can be a different treatment. One is for high Reynolds numbers, and another for the low Reynolds number. At high Reynolds number, this k epsilon model gets valid, but it's not necessary to solve all through to extend to the wall. So near to the wall, we can use universal law behavior for values between 30 to 150. We can use these expressions, not necessary to make solve those areas where boundary layer effects are taking into effect for the high Reynolds number flows. So k is one common constant, or roughness parameters are being empirically identified, and this is for higher Reynolds number. For low Reynolds number, the law universal wall behavior is invalid, and there should be certain modification should happen in the k epsilon module. The reason is the damping effects of the viscous has to be improvised into this model to make sure that viscous stress take over from the Reynolds turbulent Reynolds stress at this low Reynolds number flow. So there are certain modifications on all these three expressions. One is for the turbulent kinetic energy, that's a turbulent viscosity, where we add an additional term called f mu, and k and epsilon are also added viscous effects into this gradient divergent diffusion terms. So these additional constants are modeled through the turbulence Reynolds number, which are expressed through this k and epsilon values. So the performance of this k epsilon model is mostly valid and widely used, and it is been well tabulated and validated turbulence model compared to other models, and it's widely used where the thin shear layer effects take into effect in the fluid phenomena. So those models are particularly perform well in where thin shear layer occurs, like confined flows. So these are mainly industrial one flows. That is the reason that one of the development happens for these models. But this poorly performs in unconfined flows, like jet flows in stagnant surroundings, and also in axis and also in non-circular ducts, long non-circular ducts. So where the reason is some deficiency in the treatment of the normal stress within the k epsilon model. For that reason, for these flows, it would be better to model Reynolds stresses directly, which will be the next part of the video. So the advantage would be it's a simplest turbulence model. It will be very much excellent performance in many industrial relevant flows, and it's a well established and validated turbulence model. But it has a very poor performance in unconfined flows and rotating flows and non-circular ducts. Hopefully, we next video we see about this sophisticated version of the Reynolds stress equations, where we have 6 additional equations for each of the Reynolds stresses. Thank you.